In 4.6, we're going to use local linearity to approximate function values. So here's this statement. It says a tangent line of f of x at x equals a can give an approximate value of f of x for points near x equals a. Okay, let's think about what they're saying. Okay, first there's a tangent line of f of x at x equals a. So let's assume this is f of x. Let me pick some random point. We'll pick it right here. Let's just assume that that's the point on f of x where x equals a. Okay, I'm going to go ahead and draw the tangent line. Okay, now the tangent line can give an approximate value of f of x for points near x equals a. So if this is the graph at x equals a, right here, if I plug in the point right here on this line, and I get the value of the point on the line, that's going to be really close to the value of the point on the graph. If I go way out here and I pick the point on the line, they're saying that this is an approximation for this. Although the farther I get from A, you can see it's getting farther and farther from the line. But if I stay right near x equals A, the value on the line will be very close to the value on the graph. Okay, now they also want you to think about it considering the graph. Okay, we're going to call this graph concave up. It looks like it's opening in the upward direction, so we're just going to look at it and assume that it's concave up. In the future, we will actually have a formal definition for what concave up is. Okay, if this is concave up, and if I use the line to approximate the values, think about, will the y values on this line be a little higher or a little lower than the actual values? Okay, well, the y value here is lower than this one. Y value here is lower than this one. Y value here is lower than this one. So no matter where I pick on the line, the approximation I get is going to be an under approximation. It's going to be a little bit lower than the actual value of the function at x equals a point, whatever it is. Okay, now let's think about if the graph is concave down. This is concave down. It's kind of opening in the downward direction like a sad face. We will learn the formal definition, but for now, it just looks like it's concave down. Okay, let me pick a point, random point, x equals a. I'm going to draw a tangent line there. Okay, now if I use the values on this line to approximate the values of the graph, I can get pretty close the closer I am to x equals a, but you can see from this, the point on the line is always a little bit higher than the actual function. So if I use this to approximate, this is always going to be an over approximation because the tangent line always ends up a little bit above the graph. Okay, now let's go ahead and try it. Okay, example 1, f of x is concave up. F of 4 equals 5. F prime of 4 equals 3. What is the estimate for f of 3.8 using the local linearization for f at x equals 4? Okay, so if I'm using local linearization, I need to write the tangent line for the graph at x equals 4. Okay, so at f of 4, the y value is 5, so this is going to be y minus 5 equals, what's the slope at x equals 4? F prime of 4 is 3, so the slope is 3. X minus 4. Okay, that's the equation of the tangent line. Now, they want me to use the equation of the line to approximate a value for f of 3.8 because f of 3.8 is pretty close to x equals 4. Okay, so I'm going to go ahead. No, don't write that. Let me write at x equals 3.8. Okay, I'm going to plug it in. Y minus 5 equals 3 times 3.8 minus 4. Y minus 5 equals 3 times negative 0.2. What is that? Negative 0.6. And then if I add 5, I get negative 0.6 plus 5, positive 4.4, which means our approximation for f of 3.8 is about 4.4. And I use the tangent line to estimate this. So this is an estimate. This is not the actual value. Now the next question is my estimate here an underestimate or an overestimate? Okay, what is this? This is concave up. Okay, so if it's concave up, in your head, I'm thinking, okay, this is concave up. If I draw a tangent line, the tangent line is always lower. So this is an underestimate because the graph is concave up. And you don't really need to memorize it. You just need to always think, okay, what does concave up look like? What does the tangent line look like? And is it lower or higher? Okay, let's go ahead and try another one. Example 2. Example 2, we're given the function f of x equals 5x minus 2x to the third minus 2. We're going to find the tangent line at x equals 1 and use it to approximate f of 1.1. So I'm finding the tangent line at x equals 1. That's the first step. Do I have f of 1? No, I don't. Let me find f of 1. What is f of 1? 5 times 1 minus 2 times 1 to the third minus 2 is 1. Now I need the slope of the tangent line, so let me find the derivative of f. And then evaluate that at 1. 5 minus 6 is negative 1. Okay, so the tangent line is y minus 1 equals negative 1, x minus 1. Okay, now let me use that to approximate f of 1.1. So at x equals 1.1, I'm going to use the tangent line. What is that? 0.1, negative 0.1 plus 1. Okay, so this approximation is telling me f of 1.1 is about 0.9. Okay, now if we wanted to just test to see how close it was, we could just plug 1.1 into this expression to see how close it is and see what a good estimate is. But I don't think we will right now. Okay, let's go ahead and look at number 3. Okay, what's number 3 asking me? If dy dx equals e to the y 2x squared times the quantity 2x squared minus 5x and y equals f of x, let y equals f of x be the particular equation to the differential equation with the initial condition f of 2 equals 0. Write an equation for the tangent line to f at 2, 0. Okay, let's go back to the given. They give me the derivative of y with respect to x is this. Okay, now they tell me that let y equals f of x be the particular equation to the differential equation. They just want me to know that originally there was a function f of x. When I took the derivative of f of x, that was the same as dy dx, and then I got this. So this is the derivative of f of x. And for that same initial function, f of 2 is equaling 0. So they're just telling me this is the derivative for what was the function f of x. Okay, so what am I going to use the derivative for? The derivative is the slope, so I want to find the slope. So let's find the slope of the tangent line at 2, 0. So the slope is e to the 0, 2 times x squared. What is 2 squared? 4 minus 5 times 2. What is that? That's 1 times 8 minus 10. So the slope of the tangent line is negative 2. Okay, and then the initial condition was f of 2 equals 0. So I'm going to have y minus 0 equals negative 2 times x minus 2. Or I could have just said y equals negative 2 times x minus 2. Okay, so did I do what they asked? Write an equation for the tangent line of f at 2, 0. I did. So this is my equation for the tangent line. Okay, now let me use my equation to approximate f of 2.2. Okay, so at x equals 2.2, I will plug in y equals negative 2 times 2.2 minus 2, which is negative 2 times Negative 0.4. Okay, let's do, which is telling me that f of 2.2 is about negative 0.4. And in this case, I don't have the original function, so I don't actually know how close I am, but it should be a decent approximation.